All right, there we go. Any questions before we get going? We officially have more than half the people here today now. Wow. Wow, I know, right? You should clap for yourself. Yeah. No questions or anything? No? Oh my God. Another person. It's popping in here. Holy moly. How close are we to? How many are we over half? 1, 2. We're 2 over half now. Yeah. Because when one person walked in, I was like, oh, we're actually at half. Oh no, we're over half. And now we're just only over half. Anyways. All right, seeing no questions and joking about attendance aside, let's carry on. Okay, last time. So we built the sphere class. I mean, look, we started making our own classes. We defined a circle class. And then we made a slightly more sophisticated class, the sphere class. And why was it more sophisticated? Well, we added a couple of attributes, and then we added some functionality such that spheres could kind of interact with each other directly, right? I have 2 sphere objects. How can they interact? We can ask one, well, how far away are you from some other sphere, and so on. And then we added some those special magic methods, right? We added the repr. We added the equals. Equals was to define, or well, underscore, underscore, EQ, underscore, underscore. That's how we defined equality. And remember, you don't call these magic methods directly. We invoke them through some other way. For example, when we use our comparison operator, equals equals, between 2 objects, it just goes and calls the EQ method for us. It's just nicer syntax. We don't call the initializer constructor directly. We just call the name of the class. We don't call the repr directly. We call like stir, or we print out the thing, right? These methods get called like indirectly. And they're nice methods. But what was interesting about those methods is, whether we wrote them or not, Python gave us free versions of those methods. They weren't necessarily helpful, but they did exist, which was interesting. So, okay, we've got a sphere class. And, okay, before I carry on, any questions about any of that? Okay, we have our sphere class. But, if I'm making spheres, maybe I'm writing a program to define several different types of 3-dimensional shapes. And, with a sphere has an x, y, z. If I wanted to define, to define a sphere in some 3-dimensional space, what do I really need? I need a center point and a radius. Now, if I wanted to define a cube, what do I need? Well, okay, let's say it's not really a cube. Let's say it's some no, let's call it a cube, right? A cube. A cube has a side length, and if it's a cube, they all have the same side length, right? So all I really need is a single point. And with a single point, I can, I guess with a cube, I can maybe use 8 points? Whatever, the point I'm making is, I might need x, y, z coordinates. If I'm making some pyramid, I'm going to want x, y, z coordinates. And we might start to get a feeling look, whenever we were writing code and we found ourselves repeating functionality, we would extract that functionality and put it into a function, and then we could call that function whenever we wanted. I didn't need to explicitly write the code to do something over and over and over again. I can just put that code into a function, and then call that function whenever I need it. But with classes are a higher level, objects. They're a higher level of encapsulation, where not only are we just capturing some functionality, we have some functionality and some data going together. So you might get a feeling okay, if my sphere has an x, y, z coordinate, x, y, z coordinates, and my cubes are going to have x, y, z coordinates, maybe it makes sense to kind of extract that x, y, z out. And that's exactly what we're going to do. If I could extract that x, y, z out, and kind of put all the x, y, z stuff over here, I still have my sphere. A sphere will still know its x, y, z coordinate through having some way. But if I've got like that x, y, z functionality and data extracted over here, I can make use of it in other parts, like for cubes and pyramids and spheres. So that's what we're going to do. I'm going to make a point 3D class that's going to just be the definition of some point in three-dimensional space. It's just going to be an x, y, z coordinate with some functionality. A lot of this functionality that I'm about to write already exists in our sphere class, but the point is I want to like extract it out of our sphere class and put it over here. And then our sphere class can make use of the point 3D class. I feel like this is best learned with the example that we're about to see. Any questions on the idea, though, before we jump into this? All right. So, okay. There's nothing wrong with the original sphere. Excuse me. But this will make our sphere class simpler and easier to understand, and it allows us to write methods at a higher level of abstraction since we can deal with point 3D objects instead of individual coordinates. You'll see what I mean. If we want to make other three-dimensional shapes, they can use something like a point 3D class to represent their position, and it allows us to abstract and delegate some functionality to another class, and it will help with testing since we can test the point 3D class's functionality independently from the sphere's functionality. So let's start making a point 3D class. The purpose is to basically deal with all that coordinate stuff from the sphere class. So let's make a point 3D class. The class will also have a few methods. A method for measuring the distance from another point 3D object, check if they're equal, and we can get like a string representation of this class. So that's what we want to extract. So let's start with class. Whoops. There, we're starting our class. There, that's it. That's all we really need for our constructors for the sphere class, or the point 3D class. What do? Well, we've defined the class point 3D. Oops, I think I actually called it point 3 uppercase D in my example. Yeah, I do. I guess I'm going to want this later for square root. But there we go. All this is, okay, we are defining a class. It's called point 3D. And within that class, we are giving it our own initializer, constructor, that says, how do I create this object? Well, all we're going to do is give it 3 values and assign those values to the class's attributes. The x, y, z coordinates that we get as the parameters are going to be set to the instances, like, okay, the x's, y's, and the z's of that instance. Happy, sad? Give me a thumbs up if you're happy. You're tired. You could still be happy, though. That's it. We've got our point 3D class. You'll note in this example I've got some type hints. Okay, that's nice. Now, methods. Well, what methods do we want? Well, we want a way to measure distance between points. Now, we actually already implemented this in the sphere class, but let's just re-implement it from scratch, because why not? So, def distance between, or distance from point, all right. Call it other. Okay? And what are we going to do? Well, it's Euclidean distance, right? So self.x minus other.x squared plus self dot y minus other dot y squared plus self dot z minus other dot z squared. I think that's it. Does that look right to you? Maybe I'm wrong. I don't know. There we go. Euclidean distance. Great. And if you don't trust me that that's Euclidean distance, well, maybe I made a typo, but I think that's right. If you don't believe me, go look it up later. All right. Happy? Sad? What do we like here? Yes?
So the point 3D class, how does that relate to like a sphere class? Are they connected in a way?
They will be. We're not there yet. Okay. We're about to get there. Okay. Yeah. But yeah, your brain's going asking the right question. We're going to have to rewrite the sphere class. Yeah. Other questions, comments, concerns? I mean, this is all I really need at this point. We want our EQ and our repr. So def EQ. What should it mean for 2 points to point 3D objects to be equal? Well, first we should say, okay, if is instance of other we'll just say, okay, if it's not a point 3D, they're not equal. But what should it mean for these 2 points to be equal? Well, probably if they exist at the same point, right? If the x's are the same, the y's are the same, and the z's are the same, chances are we're good. So if self.x equals other.x and self.y equals other.y and self.z equals other.z. There. I think that's pretty good for the equals. What do we think? Can you think of anything else that would make sense here? I can't really. I think that's basically, I think that's all we could really expect. And then a repr. What should our repr look like? So what should the string representation of this class look like? Well, we have a couple of options. It's entirely reasonable to be like, well, you have like a three-dimensional point. So you could do something like this. Right? Kind of make it look like a x, y, z coordinate, right? That's how we would write a coordinate, right? So that's entirely reasonable. For your needs, that might make sense. Now, I'm not going to do it here because, one, it's going to be confusing with a tuple. And we have a simple fix to make this a little bit more clear. Is what's that basic pattern? Well, I like put the name of the class out in front of it. That way, you know, there, x, y, z, cool. If you're the type of person that would like it to be a little bit more explicit and like, well, what's what? You could be like, okay, x equals, y equals, z equals. And there we go. Just as a review for like, wait, what does this translate to really? Well, let's go create a point 3D object. A equals, let's call like a point equals 1, 2, 3, and then print a point. Well, now we see point 3D, x is 1, y is 2, z is 3. So now when I print it out, I know what the class is, it's named right there, and I know what its attributes are I care about, they're right there. If you feel that this is entirely unnecessary to include that for your needs, well, that's fine. But if I hit run, we will lose the x equals, y equals, and z equals, of course. Questions? This is all good? Happy? You have a question? Looks like you have a question. You sure? It looks like you might. No? How about you? Do you have a question? No? All right. So everything we've seen so far is effectively review of what we've done already. We did this with like the circle class. Although with the circle class, we didn't do EQ or repr, but whatever. We defined the class, made the instance. We did something very similar with the sphere class, define the class, have some attributes, methods. Then we added these magic methods. And now we're doing it with point3D. Define the class, define the constructor, assign attributes, or create the attributes, write some methods, include some magic methods. There we go. Cool. But I was getting at that whole idea of like, okay, well, I've like extracted this point3D concept out of the sphere class. So how does this connect back to the sphere class? Well, let's see. Yes, repr, cool. And I could write tests for something like this. And before we actually go back to the sphere class, one thing I want to impress upon you is these tests are starting to get, like, look, let's look at these tests. Let's make sure these tests make sense. First, we can't just start writing assert tests like we did with functions, because we can't start testing an object before it exists. So we have to like start with some setup code. I created something called point origin. It's a point3D at 0, 0, 0. We verify that the attributes give me back what I want. I verify that the point's distance from itself is 0. I verify that its distance from some other point at 1, 1, 1 is that. Same with, I guess, in the negative direction. And I check its toString, its repr, pardon me. Down at the bottom, I have some equals tests. What else? And then I'm creating another test for point3D with different like attributes. So this is kind of funny. So first of all, this is getting verbose. Would you agree? Like, okay, I'm testing a class, but I can't just test the class because each class has several methods that need to be tested. So it's like I'm testing all this functionality, but they need to be grouped together because it's testing a class. And like, oh, I'm testing, like on line 5, I'm testing the distance from the point, but also on line 6 and 7, and also on line 14 and 15, I'm also doing, like, it's getting fragmented. It's not immediately clear what each test is doing like it used to be. These tests are getting kind of hairy. And it's because we are getting to the limit of how, I don't want to say that these assert tests aren't useful the way they are, but I am hitting a limit in terms of how this style of testing starts to become slightly more painful as our programs and our code grows in sophistication. Still valid, still correct, it'll work for us, but this is starting to become unmanageable, and it's only going to get worse as they grow in complexity. But the good news is we have a nice way to manage tests like this in a much more like robust way, for lack of a better term, that we will see very shortly in the class. But anyways, back to the sphere. So if we go back and we look at the sphere class, we created our sphere, and it had an x, y, z coordinate, in addition to a radius. But now, I've taken the x, y, z out, and I'm going to store it in some other object. It'll still have to have a radius, though. But here's how I'm going to do my sphere class. There. That's what I'm going to do. What do I have? Self dot. Oh, yes. I have center point twice for some reason. Good catch. That would have been confusing. There. Much better. So I've defined my class. It's a sphere class. But how is it different than from last time? Well, the last time, the sphere took x, y, z, and a radius. But now it just takes a center point, which is going to be a point 3D object. So it's going to take a point 3D object that has an x, y, z coordinate inside of it and a radius. Okay? That's how we're going to do this. Okay, what do I say? From looking at the above code, we see that we have effectively removed the x, y, z from being like explicit attributes of the sphere class. Because, I mean, they're still there. We wrote the point 3D class. We know that the point 3D class has an x, y, z attribute. So if the sphere has a center point attribute that has an x, y, z coordinate, well, effectively, the sphere class still has the x, y, z coordinate, but it doesn't have it like directly. I mean, it is still directly, but it's not like as explicit as it was before. Okay, instead we make use of point 3D object, and as we know, those coordinates exist there. So let's start writing the methods. Well, okay, our diameter, surface area, and volume, those don't change. They're all just based on the radius. The center point doesn't matter at all with these methods, right? No x, y, z is important for these methods. That's fine. So far, so good? So far, so good. Now, once we start to get to distance between centers, it's a little funny. How do we do this? How are we going to do this? Well, look, we know the expression is going to be like, okay, well, return math.sqrt of self dot, but we don't have a self.x anymore. We have a self.centerpoint.x minus other.centerpoint.x, and so on and so on and so on. But what do we also have in the center point class? We have a method that calculates the distance between points. Oh. So why don't I just say, hey, my point, my center point, nope. How far are you from the other center point? So now I have entirely offloaded that functionality to the center point, or to the point 3D class. The sphere asks its point to figure out how far away it is from some other sphere's center point. The point class is doing all of the work. The value is returned to me. That's fine. That I then just pass on to you. But this class delegates all of that like x, y, z coordinate functionality. That distance functionality is delegated to an entirely different class. Is this clear? I hope it's clear, because this is pretty damn cool. Okay, so no, yeah. Now, I mean, now the other methods are actually the same as they were, because they just delegated to this method, right? So remember, like distance, what was it, like between edges? Well, this is the same as it was before. Because this method delegated to the distance between centers method. This is the distance between center method, but now instead of actually doing all that calculation for the Euclidean distance, it delegates all the work to its center point's distance from point method. Cool? I think this is pretty cool. And then def there. Oops. Looks pretty good. By the way, be very careful, because whenever you call a method that exists, whenever you call a method, it needs to be like prefaced with its implicit argument, which is like a reference to the instance that you're calling it on. Long story short, if you were to say this, we'll call the method distance from edges, you can't. You need to say self.distance from edges. Like that, you need that. Okay, you seem to have a question? Yeah. Maybe I've done something wrong. Maybe you caught something.
Well, you were just using other instead of other dot center point as your inputs for distance between edges and overlaps, and I'm just wondering.
Here's why. Because
Doing the raw point 3D is fine.
here's why. Because other, in this context, other is going to be a sphere. Okay? So let's say I call overlap. Let's follow this through. I call overlap. Self is a sphere, other is a sphere. So I want to know, hey, call distance between edges on other. Check if you overlap with this other sphere. But we call distance between edges, okay, so we call this. And then we call, well, distance between centers. Well, I want to know how far apart the center are of this sphere and the other sphere. And minus the radius and the radius. And then distance between centers, well, distance between centers takes the sphere. And then we say, okay, well, my center points, which is a point, how far away are you from another point? Whose other point? The other's center point. So good observation. So here is where I really, like this was perfect. It could almost be staged. I promise you this was not a staged question. Was it staged? No, it was not. So this is where I think I should have been doing type-ins, right? But with Python, I don't really need type-ins. But I probably should have been doing type-ins. But at the end of the day, type-ins don't enforce anything. They're just there to help the programmer. It's just like, it's like having your syntax being even more self-documenting, which is great and all, but it doesn't enforce anything. And I know I complained about this earlier in the semester, and I probably complained about it, I peppered throughout the semester. In my opinion, I'm going to go on a rant, so buckle up. Who just said, uh-oh? It won't be that bad. So, a lot of people are like, Python is great for learning. It's a great programming language for learning. And with that statement, I don't disagree with 1,000 asterisks. I think it is a fantastic language for this stage. In fact, actually, let me fix that statement. I think it's a fantastic language for learning the core concepts, your values, your types, your variables, functions, ifs, Boolean comparisons, ifs, loops, linear data structures, classes. But as I went down that list, my enthusiasm for Python wanes. Like, we're at the stage where I still won't say Python isn't great for learning these concepts, but we are hitting the limit of what I think of Python's value for learning to program. And it gets to the point where Python, I think, gets in the way of learning. We're about to hit that like inversion point of going from Python's really great for learning these concepts to Python starting to get in the way of you learning these concepts. Because Python's nice, that niceness is bad. So, don't worry, next semester we're getting rid of Python, which is a good thing. I don't care how much you, like, people start the semester saying, I wish this was Python still. By the end of the semester, I don't think I've ever heard a single student say, like, yeah, I wish this was Python. That would be a terrible idea in my opinion. Some universities carry on Python through 162, their version of 162, which I think is a horrible idea. I think you would learn less because of it. You would spend more time being angry at your computer. So next semester we switch to another language, Java. Don't get me wrong, I have a laundry list of reasons why I don't like Java too, right? But Java addresses a lot of, just one sec. Java addresses issues. Java kind of forces you to do things a certain way that makes you have to be like very explicit with everything you do. And one of those things is the typing, where you have a parameter, you have to tell Java, what is the type of this thing? It's not a type hint, it's a requirement of the language that you specify. And if all of these types were laid out explicitly, so much so that the language enforced, like remember that example I showed you where I'm like, it's a function that takes two integers and returns their sum. But if you accidentally give it strings, it just concatenates the string. So 1 plus 1 is 11, right? If this was Java and you said, take the integer A, integer B, add them together, it would not be possible to make that mistake of giving it two strings. Java, it's not even like Java would crash. Java wouldn't even start running, which is a good thing. It's better to have incorrect code not run at all than run and fail. It's better to not run at all than to run and be wrong. So, if this was a language like Java, which in like a month or 2 months, month and a half, whatever, we're going to be switching to, if you're in 162, this would be a lot more clear. And Java does a really good job at making things a little bit more clear, because you have to go out of your way to be a little bit more explicit about everything. And what were you going to say? I have a problem with every language, yeah. What's my ideal language? Well, there's a common joke that, of course, I can't remember the wording of right now. Let's see if I can find it. Let's see. What was it? What's that one? No. I wish, for some reason I can't think of it, it's because I'm putting myself on the spot. But there's a quote by like a famous computer scientist that's like, well, there's the good languages that everyone loves, and then there's the languages people actually use. Meaning like, everyone hates all of these languages, but they're the only ones we use, and for good reason, right? So like, everyone complains about the good languages, really. These idealized languages, there's no such thing as the best language, for better or worse. It's kind of funny. What I would say, and I am by no means an expert in this type of stuff, but like, there's kind of like generations of programming languages. You go way back in time and you're programming in like machine languages, okay? Like punch cards. Anyone in here know what a punch card is? 2 people, all right? A punch card is a physical card that you would punch holes into that represent On, off, on, off, on, off, right? And the configuration of those switches, basically on, off, would configure the computer, because the computers are like very mechanical things, of like whether or not certain things are activated and deactivated all at once. These are concepts you learn like next year, by the way. Like how the computer actually works. So people are programming, like physically programming on these punch cards. And that's where like the word patch comes from. Is if you've got a punch card and you punched a hole in it and you didn't want a hole to be there, you put a little patch in there. You patched your code, which is funny, right? Anyway, so you'd have all these punch cards that were your program, right? And people would show up to these computers that are really slow. You wrote your program, and like today when you write your program, you make some changes, you hit run, it didn't work. You make some changes, you hit run, it didn't work. You make some changes, you hit run, it didn't work. This is how it used to work. You'd wait a week, and your scheduled time at the computer in the next town over was available for you. So you get there, and you've got your box containing all of your cards for your whole program. You take them out, and you drop them on the ground, and oh my God, what have I done? Now they're out of order, and you're never going to get it figured out. So you collect them all, you go back home, you reschedule your time, you get them in order, and next thing you know, it's 2 weeks later, and your time at that computer is available again. You get there, you take your program out of its case really carefully so you don't drop anything this time. You put it in the computer, you hit run, and it doesn't work, and you go like, F. All right, well, let's go back home. You go back home, you make changes to your code. It's 2 weeks go by, you're turning the computers back, so you go to the, it's socialized computing, right? You go for your turn at the computer, you put it back in, you hit run, it still doesn't work, okay? And a year later, maybe your program works, right? Like that's how it used to be. Now you just hit run until it works, and that's a good thing, right? But that's a little different. And this wasn't even that long ago, by the way. So, machine language. And then after machine language came assembly, where basically it's like the most primitive form of of a sophisticated programming language, where we basically use like little like tags that kind of like mean like add means like 01000110, which means like add these two numbers together or something, right? So we got assembly. And then after that, all the other languages started to arise. You had these early languages like Fortran. And these early languages, they all kind of like came out at the same time. You had like Fortran. And one of these languages would do something like really like groundbreaking. Like inventing types. Oh my God. Before, there were no types. There were just zeros and ones. But then suddenly data had like types associated with it. Well, that's great. Then all these languages existed. And then like another generation of languages come along, like C shows up. And it kind of like sets the groundwork for the syntax we use today. Python is like a C-like language. The syntax we use in Python is like inspired by C. And then some time goes by, and then maybe some languages start to like incorporate, like they shove some stuff in there, like a language like C++ comes along, which was C with objects, but they were just kind of like hacked onto the language. They didn't work that great. I mean, C++ is still around today. It's a fantastic language, but it's limited. But then new languages like Python and Java showed up in the like early 90s. So like this is like the timeline here, right? In the early 90s. And this was like a new generation of languages where the ideas of like objects were actually like built into the programming language as like a core thing. And then some time went by and we started to learn some things like objects kind of suck and all this stuff. And then we started learning like mutability is terrible. So we started shifting like functional languages, and there existed other functional languages. And then there's been like a new generation of language where you have things like Kotlin and what? Rust. Yeah, Rust. Yeah, Rust would probably be in there. Kotlin, why am I, Scala or Scala, however you want to pronounce it. There's like a new generation of language that has like incorporated these newer ideas, except for whatever reason, that newer generation isn't like, we're still kind of stuck in that previous generation. And who knows if we'll ever really kind of, move. There's a reason, like if you might be like, well, you're not teaching us the newest generation of language. Yeah, you're welcome, right? Like it's great and all, it's great, but like that would be weird. They're still fairly esoteric. So like there's this like progression of languages, and they all have pros and cons, all from their different eras and whatnot. The reality is you might get a job where you're programming in Fortran. That can happen today. You might get a job where you're going to program in C. That's not weird. It's not weird. C is a great language. You'll have a job, you're going to program in C++. That's great. If you take 255, there's a 50-50 chance at St. FX you're going to take 255 and you're going to be using C++, right? 162, you'll use Java. You might get a job using Java. Like, they're all similar and different in their own ways. Now your C, C++, Java, Python, they're so goddamn similar in terms of syntax and how you interact with the language, which is a good thing. But they all kind of have pros and cons. Java has a lot of pros and a lot of cons. C++ has different pros and different cons. It all kind of comes with like whatever. So that was a long-winded answer to your question. What language do I like? They all suck, yeah. Yeah, what?
Would you say that C is the first one that just like, didn't completely suck?
No, C completely sucks. No, C was like at like a crossroads, let's say, of, okay, we've made something that didn't suck, but we have no guardrails. So it's like this like violent, terrible world where where you will get eaten alive by each other and the language, right? Like so like it was fantastic, and then it was like a dystopian wasteland. That's what C was, I guess. Yeah, that's a weird explanation, but I'll go with it. Yeah. Other questions before I carry on? Okay, rant over. All these languages are a little different. Anyways, C or Java could have helped eliminate that particular thing because the language has something built into it that like forces us to be more clear and makes everything slightly more coherent. But one of the things people will complain about with Java, which is entirely true, is so with Java you have to be a little bit more verbose to be like more explicit about everything. And a common criticism of Java is it's so goddamn verbose. Just shut the hell up. Like that's like what people will say about Java, which is entirely fair. So, you know. All right, there we go. Now, here's something very interesting. Let's write our equals method. Well, all right, so we are saying, first, if it's not an instance of a sphere, it's not a sphere. If it is, well, let's start doing our comparison. If it is a sphere, well, compare the radius values, but then notice I am not comparing x, y, z coordinates directly. I am comparing my center points. But how does Python know how to compare center points? Well, a center point, that's a point 3D. So I'm using the comparison operator on a point 3D object. How on earth does Python know, I keep trying to say Java, how on earth does Python know how to compare point 3D objects? Because I told it to, with this. So, if I ever use the comparison operator on two spheres, the sphere will be like, hey, let's say I'm comparing me and you. What's my radius? What's your radius? And then I go, okay, I also have a point 3D. Here, point 3D, figure out if you're equal to that point 3D. And then they go figure it out, they tell me, and then I can tell them. I've delegated the equality of one of my attributes to its equality. In fact, how the hell do you think, like I used x. X was just like a float for a radius. How does Python know how to compare floats? I've been using equality on floats this whole time. I wonder if there's something like an EQ method for floats. Oh my God. Right? This is all how it works. It's all these layers of abstraction. Cool, right? And we're going to use the same idea with the repr. But check this out. So let's go do the repr. So what is the sphere's repr? Well, say sphere, center point, and then get the center point, and then radius, get the radius. But hold on, what's the string representation of a center point? Well, here, let's make a sphere first of all. It wants like a... And look at that. sphere, center point, and then it's the point 3D. If you don't trust me that when I call the sphere's repr, by saying like print it out, which indirectly calls the repr, remember that, this is calling the point 3D's repr. And to convince ourselves of that, we can change this to be something silly. And when I hit run, we see the center point is now blah, 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 because we changed it to do that, which is, of course, nonsense, so we'll put it back. But now, like, this functionality is like cascading. Object has a reference to another object. I just delegate, okay, oh, you want the string representation? Like, you want the string representation of me? Okay, well, here's how I do it. First, I take, okay, I'm a sphere. And then I need the point 3D string. What's that? What's the point 3D? Oh, okay, great. And I need the floats. What's the floats? Oh, okay, great. And I stick it back and then give it over there. It's the same as when, like, a function calls another function, which calls another function. Well, now we have an object that can call in something about another object and another object. It's just like another layer where I'm not just having a function call some other functionality, call some other functionality. I've got objects, which are these like this encapsulation of data and functionality calling data and functionality, calling data and functionality to do something, which I think is pretty cool. You might, so when looking at this, you may have thought to yourself, you know, your initializer takes a center point, meaning some point 3D object must already exist that's given to this sphere upon creation to be saved reference to. Could I not do something like this? Could I not do something like this, where the sphere still takes an x, y, z, and then in the constructor, it goes and creates its own instance of a point 3D object? You may have thought, why not do that? You are entirely right. Why not? That's entirely reasonable to do it that way. Now, don't get too excited, because I would still, it's entirely reasonable, and for whatever reason, this might be a really great design decision for your program. But if you don't need to, if you were given a choice where, like, it doesn't really matter which way I do it, I would suggest extracting it out. It's always good to, like, extract dependencies, meaning, like, this object would then, like, the creation of this object would be responsible for the creation of another object. There's nothing wrong with that, but it's almost like, it's hard to explain, especially at this stage, but it's almost like if you've got your flow of your algorithm, it's better to have your algorithm go create a point 3D, right? And then you give that point 3D to some other sphere. No, let me redraw this. It's better to have like your flow, like imagine this is your main, where your main says, go create a point 3D, get the point 3D back. Give the data you need to make a sphere, get the sphere back. There's like a good reason why we like that as opposed to something like this. Where like, well, the point 3, like, or maybe we could think of it more like where the sphere goes and makes the point 3. It's hard to really explain this concept at this stage. As we learn more and our programs get more sophisticated, this becomes a little bit more clear. But I'll give you a little like hand wavy, like, you know, don't inject it's kind of better to like keep the dependency of like creating something outside and have all of that dealt with like in your main, like your like the main chunk of code that's calling everything. have it deal with all of that stuff as opposed to like you guys passing it all around to each other. I know it's hard to wrap your head around it, but there's a good reason for this. There are cases where it's not always true, but you know, if you can, maybe it's nicer to do it this way. Anyways, I'll catch you all later.